In this video, we have a look at bivariate data from the point of view of senior school mathematics. Let's have a quick look at the list of things we cover before we actually go into the video. We look at scatter graphs, so how we plot data from a table given two variables or bivariate data. We then look at the relationships from that scatter graph, and that's done mainly from the point of view of a linear relationship. We then examine the least squares regression line, or the line of best fit for that data. Then we examine the correlation coefficient and possible values for that. We also look at predictions based on our line of best fit and the residuals that occur from that, and we talk briefly about the coefficient of determination. So now let's have a look at a table of bivariate data. And the first question we should be asking ourselves is, why is it called bivariate data? Well, we can see in this case that we've got two variables. We've got numeracy, which represents students' score in a numeracy test in mathematics, a branch of maths, and we've also got student score in space, another branch of mathematics. So for example, we might have a student score 12 in numeracy, and the matching score in space was 16. Another type of data that we regularly see is called univariate data. In this case, we might have student scores in the numeracy test, or perhaps they're represented as a frequency table. In this case, we can see that one student scored 12, whereas two scored 15, one scored 7, and three scored 18, etc. So let's have a look at the bivariate data again, and this time determine if there's some sort of relationship between the numeracy scores that students achieved and their space score. We can start doing this by having a look at a scatter graph of the data. So let's examine how we actually plot these scores onto a grid to form the scatter graph. Now what we'll do is we'll place numeracy on the horizontal axis and we'll place the space score on the vertical axis. In this instance it doesn't really matter, but what we try and do is place the explanatory or independent variable on the horizontal axis and the response variable, in other words something that occurs as a result of the independent variable, on the vertical axis. So let's start plotting some points. So we can see that the first score that we've got is 12 for numeracy, and the first space score is 16. That's one student. So we go along to 12 on the horizontal axis and go up to 16 on the vertical axis for space, and that's where we put our dot. The next student has a score of 15 in numeracy and a matching score of 13 in space. So we proceed to do that for all of the points from the table until we've completed our scatter graph. Once we've proceeded through this and plotted all our 8 points as we're doing now, we can start to make some casual observations about the trends in the data. If we look closely at the points, they seem to follow some sort of increasing pattern, in the sense that as the numeracy scores increase, so do the space scores. And if we circle all the points, we can see a general trend in our graph, which is what we call a positive trend. So as one score increases, so does the other. We can also talk about the strength of the relationship, in other words, how close the points are to a line of best fit. And we'll have a look at a way to describe that and give an accurate line shortly in the video. Let's have a look at those points again. This time we've highlighted them in darker circles here. And what we'll do is we'll put in a line of best fit as we see it from our own eyes. So it's not the most accurate, but it's something that looks approximately correct. And we can say approximately correct because we have an even distribution of points about the line, some above, some below, and some appear to actually fit right on the line. One of the benefits of a line of best fit is it allows us to make predictions. So let's say for argument's sake that a student sat the numeracy test but was absent for the space assessment. Let's say as well they scored 11 in numeracy. So we'd find 11 on the numeracy axis and take a vertical line up to the line of best fit, and then from there take a horizontal line to see where it meets the space axis. And we can see from our graph here that that would allow us to predict approximately that the student would score 12 in space. To show a predicted score, we use the notation y hat, and that basically means we're predicting for a y score, in this case space on the vertical axis, and we put a little symbol above that y, an upside down V, pronounce it as y hat, and that's our predicted score. In this case, y hat equals 12 based on a numeracy score of 11. We'll now go through a means to find an accurate line of best fit, and to do that we'll use a Casio ClassPad. The first thing we do on the ClassPad is we go to Statistics and we enter our scores into List 1 and List 2. We can see numeracy has gone into List 1 and space into List 2. Then we go to the menu at the top of the screen and go to Calc, Regression, Linear Regression is our next step. And then we just check to see that we've got X scores in list 1 and the Y scores in list 2. In other words, the independent variable in list 1. And for later use, we may want to copy the formula into Y1. So here's our line of best fit done accurately. We can see that the line is written as Y equals AX plus B, and the A and B values are shown on the screen. Normally we round these off to up to 4 decimal places. So our A value is 0.5948, and that represents the gradient, and our B value is 5.5139, and that represents the y-intercept. Now the correlation coefficient measures the strength of the relationship, and in this case it's 0.8112. But what does it actually mean? Let's have a look at some examples as to how we actually use the correlation coefficient. The correlation coefficient is based on a scale that goes from -1 to 1, and the extreme scores of -1 and 1 indicate perfect relationships, and 0 in between indicates no relationship. So let's have a look at some of those in terms of a scatter graph. So here first up we've got a perfect positive relationship. So if we've got a set of points which match a straight line and have a positive gradient, the correlation coefficient is 1. Now as the points start to deviate from the line, we say that it's a strong relationship, still in a positive direction, so as one variable increases, so does the other, but the points are slightly away from a line, and a correlation coefficient figure between 0.7 to 1 indicates that strong relationship. If the points deviate further from the line, we still say it's a positive linear relationship, but we describe the relationship as a moderate one. So a correlation coefficient figure between 0.4 to 0.7 would reflect a moderate relationship. Now as the points disperse further away from our line, we describe this as a weak relationship. You can vaguely make out the line is still moving in a positive direction, and a correlation coefficient between 0.1 to 0.4 would be described as a weak relationship. We then have a situation where the points are scattered randomly, and certainly from a diagram point of view it's very hard to make out any direction that we could match these points in terms of a line. So we say there's no relationship, and that would be a correlation coefficient approximately 0. Now we're dealing with negative correlation coefficients. It's the same situation as in the positive direction, but now we have a line sloping in the negative direction. And we can see a set of points here that are dispersed about a line, but one that's moving in a negative direction or has a negative gradient. And that would be values between -0.4 to -0.1. As the correlation coefficient becomes more negative, in other words in this case between -0.7 and -0.4, we have a moderate negative linear relationship. And again, this is a mirror image of what we saw in the positive direction. And we can continue that to a strong negative linear relationship as we approach -1 for the correlation coefficient figure. And then a perfect negative linear relationship is where the points form a line, but this time with the gradient going in a negative direction. So once we've got our line of best fit for our scatter graph, how do we actually predict scores? Well, in this case we'll use the same example we had before, where we've got numeracy scores and space scores for a maths class, and we've got our equation which represents the line of best fit, and we're going to predict a space score given the numeracy score was 10, and then another space score given the numeracy score was 20. So here's a quick snippet to remind us of how we actually do this on our class pad. The key thing is here to make sure that we arrange for our equation to be placed in another area of the class pad so we can do some quick substitution. So once that's set up on the class pad, what we do is we go to Graph and Table, and because of what we've done beforehand, we'll find the equation is placed there. And what we want to do is substitute, first of all, an x number, which is the numeracy score, equal to 10. When we do that, our y score, which is the space score, comes out to be 11.46, or approximately 11.5 to 1 decimal place. We'll do the same thing for an x score of 20. So in other words, when a student scores 20 in the numeracy test, we expect them, based on the line of best fit, to get a score of 17.4 in the space test. Of course, that's been expressed to 1 decimal place. These two predictions do need to be interpreted in two different ways. In the first instance, we've got a numeracy score or an X score of 10. And this process is called interpolation of data. And what that means is the X score of 10 is amongst other X scores. Some of the scores that we were given at the start of this video are higher than 10, some are lower than 10. In other words, X equals 10 is amongst the scores, and we can be quite confident with this prediction because the points are close to a line, so our correlation coefficient is quite strong. When X equals 20, this is called extrapolation of the data. And what that means is that the numeracy score of 20 in this case is above all the other scores. You might also find extrapolation could be when the given X value is below all the other scores. And because this involves a prediction outside of the given data, we're not as confident. And in fact, the further away we are from the scores, the less confident we can be. So extrapolation is something that does create doubt when we're doing predictions based on a line of best fit. The reason for this is because we're not sure if the pattern of the line continues beyond the given points that we have in front of us. Talking about our line of best fit, sometimes the correlation coefficient figure near 1 or near -1 isn't always a great indicator of whether or not a line is the best model. Let's have a look at our graph that we drew before for these points. And what we'll do is we'll examine the residuals. Now residuals are the vertical gap between the point and the line of best fit. The way we calculate the residual is we look at the Y value for the actual score and we subtract the predicted Y value, which is that on the line. We can show that visually with these vertical lines. Each one of these vertical lines that we're drawing here in green represents a residual. So we've got a positive residual, two negatives, a positive, then another negative, and then finally a positive residual. Now let's have a look at what happens when we have a set of points that are clearly not in the form of a linear graph. These are of some curve shape, and what we'll do is we'll have a look at the residuals here. So we've got a positive residual, then a small positive, then we've got a series of negative residuals, and then we've got two positive residuals. Now to be a good linear fit, what we want is a random scattering of positive and negative residuals, and that will indicate that a line is the best model. If we have a pattern that's occurring with our residuals, as we can see here in this graph, that would suggest that a linear fit is not the best way to go. So to summarize that, to be a good linear fit, we're also looking for a random spread of positive and negative residuals on our graph. We can also examine the residuals via a table. So here is our original table in the first two rows for the numeracy and space scores. And then you'll see in the third row the predicted Y scores or predicted space scores based on our line of best fit. To calculate the residuals, what we do is we calculate the difference between Y and Y hat, or in words, that's the difference between the actual score and the predicted score. So in the first case, it's 16 minus 12.7 gives a residual of 3.3. Now whilst we are looking for a random scattering of positive and negative residuals, it is worth noting that in this table the numeracy scores are out of order. So we do have to be careful if we're looking for that feature of random scattering of residuals that our numeracy scores are also in numerical order. The last thing we'll look at in this video is called the coefficient of determination. This is basically the correlation coefficient squared. We can express this as a decimal or a percentage, and its meaning is based on how it relates between the two variables. In this case, we can say because r squared is equal to 0.658 or 65.8%, we can say that that percentage of variation in the space scores can be explained or accounted for by variation in the numeracy score. Now it does not imply causation. Causation is where one variable causes another, and the correlation coefficient does not prove that. It just proves that there's a link between the two variables. So what the r squared value is saying is that if the numeracy score changes by a certain amount, you can expect some variation in the space score. In fact, 65.8% of the variation can be attributed to the change in the numeracy score. It doesn't mean that there's necessarily one causing the other, but there's certainly a link between the change in the two variables.